Okay, now we are ready to discuss the second case where we have complex eigenvalues. Now let's consider this example. Again, we have a system of differential equations. This is a 2 by 2 system, and we are given the corresponding matrix A, which equals to 1 to negative 2 1. Now the first step is to calculate the eigenvalues and then the eigenvectors. In order to do that, we want to calculate this A minus lambda I matrix first. Okay. If you calculate this A minus lambda I matrix, you should get 1 minus lambda, 2, negative 2 and 1 minus lambda. Okay. As a good practice, always write down this A minus lambda I matrix. Now the next step is to get the characteristic equation from this. So basically you want to calculate the determinant of this matrix and set it equal to 0. Now as a shortcut method, we know how to calculate the characteristic equation for a 2 by 2 matrix. So basically you should get lambda squared minus, and then trace of this matrix A, trace equals to the sum of the diagonal elements, which is 1 plus 1, therefore it is 2, plus the determinant of this matrix, which equals to 1 times 1 is 1 minus negative 4, which is 5, equals to 0. Sorry, I think I forgot to write lambda here. So basically this is a quadratic equation. Lambda squared minus 2 lambda plus 5 equals to 0. Now if you want to find the lambda values, you could use a quadratic formula, and if you do that, you should get lambda equals to 1 plus or minus 2i. In other words, now we have complex solutions for the eigenvalues, and whenever we have complex eigenvalues, they come with pairs, so conjugate pairs. If 1 plus 2i is a solution, then 1 minus 2i must be the second solution. Now even though this looks complex, it is very easy to solve the corresponding system of differential equations. What you need to do is you need to consider one eigenvalue and find the corresponding eigenvector. So now I am going to consider, let's say lambda equals to 1 plus 2i. I am going to consider this eigenvalue. Let's go ahead and find the corresponding eigenvector. I hope you all are comfortable with finding eigenvalues and eigenvectors by now. So basically we need to solve this equation, A minus lambda I times vector v equals to 0. Okay, and this is lambda 1. We have A minus lambda I matrix here, and my lambda equals to 1 plus 2i. If you do that, you should get 1 minus 1 plus 2i, then 2, negative 2 and 1 minus 1 plus 2i times vector v. Vector v has two components. Let us say they are a1 and a2 equals to 0 0. Okay, now if you simplify this, you will get negative, so 1 minus 1 is 0, but you will get negative 2i, 2, negative 2, and then you will get negative 2i. This is my I, a1, a2 equals to 0 0. Now let us simplify this matrix equation. We have negative 2i, negative 2i times a1 plus 2 times a2 equals to 0, and my second equation should be negative 2a1 minus 2ia2 equals to 0. Okay. Now, even though they look different, honestly these two equations are equivalent. In other words, if you multiply first equation by I, you will get if you multiply the second equation by I, you will get the first equation. And wait, I think I made a mistake. 2a2 negative 2a1 minus 2a2i equals to 0. Yes. So, if you multiply the second, no, this is correct. If you multiply the second equation by I, you will get the first equation. You will get negative 2ia1 and then negative 2I times I, which is I squared, and I squared equals to negative 1. Therefore, this negative times negative 1 becomes positive. So, yes, so these two equations are equivalent, and I am going to consider the first equation to figure out the values of a1 and a2. Okay. So, basically from equation 1 we have 2ia1 equals to a2. If you add 2ia1 to both sides, you will get this. Now, let us divide both sides by 2. You have ia1 equals to a2. Therefore, okay, I am going to take, let us say, set a1 equals to 1, then a2 becomes I. Okay. Let me double check my answers. Excellent. So, the eigenvector that corresponds to this eigenvalue equals to 1 and I. So, now if you want, you can get the complex solution. Complex solution x equals to, say, e to the lambda 1 t times v1, but this time my eigenvalue is a complex eigenvalue. Therefore, you will get 1 plus 2i times t, and if you have complex eigenvalue, then the corresponding eigenvector should be complex as well, and we got that it is 1 and I. Okay. So, I am going to simplify this part. It is nothing but e to the t, 1 times t is t, times e to the 2ti times 1i. So, basically what I did was I separate the real part of this one and the imaginary part of this. Okay. So, from this we are going to figure out the two independent solutions for our original problem. Okay. Now, we have found the complex eigenvalue and the corresponding complex eigenvector. For the eigenvalue, I think it is 1 plus 2i, and then we found the corresponding complex solution x, which equals to e to the t times e to the 2ti times the eigenvector 1i. Now, what we could do is we could simplify this part, and now we are going to use this Euler equation. I think we went over this in pre-calculus, but so basically the Euler equation says we can write this e to the 2t times I in terms of cosine and sine, and in this case it should be e to the t times, first we have the cosine 2t plus I times sine 2t. Then we have this eigenvector 1i. And why did we do that? Because as you know, we want to separate the real part and the complex part of this solution. Okay, so let's do that. Now if you simplify this side, you will get, okay, I am going to multiply, basically this is a scalar function and this is a vector. So if you multiply this scalar function and this vector, you will get cosine 2t plus I sine 2t that is the first component, and the second component equals to I times cosine 2t plus, okay, I times I becomes I squared times sine 2t. Great. Now let's simplify this. I squared equals to -1, and so now we have e to the t times, okay, I am going to write the real part first, cosine 2t, and then the imaginary part I sine 2t. I will do the same thing for the second component. So now this becomes the real part because I squared equals -1. So we have negative sine 2t plus I cosine 2t. Great. Now I am going to rewrite the same equation with the real part and the imaginary part. If we do that, you will get e to the t times cosine 2t minus sine 2t, okay, plus I times, which is the imaginary part, so sine 2t, and then cosine 2t. Okay, I think we need a parenthesis around this. Okay, so now we are almost done. So the next and the final step is to figure out the real part and the imaginary part of the solution, and those will give us the two linearly independent solutions for this particular problem. So now let's say x1, one solution would be e to the t times cosine 2t minus sine 2t. This comes from the real part of this solution, and then x2 equals to the imaginary part of the solution. So when we take the imaginary part, we have to omit this I. So the imaginary part would be e to the t times sine 2t and cosine 2t. Okay. I think we are done. So now the general solution x would be linear combination of these two. So we have c1 x1 plus c2 x2, where x1 equals to this and x2 equals to this. Okay. Now what is the key step? The key step is here. Once we figure out one eigenvalue and the corresponding eigenvector, we want to write down this corresponding solution, and then we want to separate the real part of that solution and the imaginary part of that solution. Once we do that, the real part will give you one solution and the imaginary part will give you another solution. And as you can see, these two solutions are linearly independent, and that form the general solution for our problem. Okay. Well, if you want, you can consider the Wronskian to check the linearly independence of these two solutions. And this is the way we solve a system of differential equation where we have complex eigenvalues. Okay, thank you.